Welcome. We're about to dive into the world of statistics. And I know that word can sound a little intimidating, but trust me, it's really just a powerful tool that helps us figure out what's real and what's not in the world all around us. And it all starts with a surprisingly simple question. So think about this for a second. Let's say someone hands you a cup of tea with milk in it. Could you, just by tasting it, tell if they poured the milk in first or if they poured the tea in first? I mean, it sounds kind of crazy, right? But what if someone swore they could? This isn't just some random thought experiment. This really happened. Back in the 1920s, at a party full of smart people, a woman made this exact claim. And believe it or not, this little argument over a cup of tea became a huge moment for modern statistics. We're going to use her story to unpack how this all works. All right, so if we're going to test her claim, we can't just wing it. We need a system. We need to turn this weird idea into something we can actually measure. And to do that, we first have to learn a little bit of the language that statisticians use to describe data. Okay, the two most basic building blocks you need to know are cases and variables. It's actually super simple. Think of it like this. Cases are the who or the what you're looking at, and variables are the what about them, the different things you're measuring. Let me show you what I mean with a quick example. So check this out. In this table, the football players, player 1, player 2, player 3, those are our cases. Each one gets its own row. And the columns, age, weight, goals, even hair color, those are the variables. This simple grid is how we start to organize information about basically anything. Now, for the next huge idea in statistics. See, in a perfect world, if we wanted to know something about a group, we just go ask every single person in that group. But you can't. It's almost always impossible. You're not going to survey every single voter in a country. So statisticians came up with a really, really smart shortcut. And that shortcut is called a sample. The population, that's the entire group we're curious about, the whole shebang. But the sample, that's the small, manageable slice of the group that we can actually study. The key thing, and this is absolutely crucial, is that the sample has to be a good representative snapshot of the bigger population for any of this to work. So this brings us to the two main jobs of statistics. First, you've got descriptive statistics. That's pretty much what it sounds like. You're just describing the sample you've collected. But the real magic, the part that's so powerful, is inferential statistics. This is where you take what you learned from your small sample and make an educated guess, an inference, about the entire population. It's going from here's what I saw in this small group to here's what this probably means for everyone. Okay, so now we've got our basic tools. We know about cases and variables, we get the idea of a sample, and we know we want to make an inference. So let's go back to our lady and our cup of tea and finally figure this out. Was she for real, or was she just getting lucky? This right here is the kind of question a statistician lives for. The way we approach this is we start by assuming she's wrong, that she's just guessing. This is what's called a null hypothesis. And then we figure out the probability of her getting it right just by pure dumb luck. So, what are the odds? Okay, let's break it down. For the very first cup, she has a 50-50 shot, 1 in 2. Totally plausible. To get the first 2 cups right just by guessing, well, those odds drop to 1 in 4. Still possible, but watch what happens. The odds start to plummet. By the time you get to all 8 cups, the chance of her guessing every single one correctly is just 1 in 256. That's less than half of 1%. And boom, that's the whole game. The result, her getting all 8 right, was so incredibly unlikely to happen by random chance that the only logical conclusion was it wasn't random chance. She actually had the skills she said she did. Her ability was, in the language of statistics, statistically significant. Now, that's a cool story, right? But you're probably thinking, okay, but so what? Why does a 100-year-old story about tea matter to us today? Well, because the exact same thinking they used to solve that puzzle is now used in things that literally save millions of lives. That simple t-test is basically the great-great-grandfather of modern biostatistics. When scientists are testing a new drug for cancer, they are asking the exact same fundamental question. Is this drug actually working, or are the good results we're seeing just a fluke? Could it have happened by random chance? And this is where it gets incredibly serious. This way of thinking is used every single day to test new medicines, to track the spread of infectious diseases, to see if public health campaigns are making a difference, and to pinpoint the things that put us at risk for diseases like cancer and diabetes. Honestly, modern medicine as we know it would just stop without this. So where does all this life-saving data even come from? Well, it mostly comes from two places. You've got primary data, which is when researchers go out and collect it themselves for one specific project, like a clinical trial. And then you have secondary data, which is data that's already out there, like hospital records or census data that we can reanalyze to find new insights. So look, if you take just one thing away today, let it be this. From a simple cup of tea all the way to a revolutionary new vaccine, what statistics gives us is a reliable, repeatable framework to tell the difference between a real, meaningful effect and just random noise. It's a way of thinking. It's a tool for asking better questions. And now you know the fundamentals of how it works. So I'll leave you with this. What's an important question about the world that you'd want to answer? What claim would you want to put to the test? Thanks for tuning in.